Okay, guys. I am going to do two problems. What I want to start with is problem number 27. So what we have is a system that kind of shows what braking system of a car looks like. So there's two sides for this. One is where you have the brake pad. The other side is where we have obviously I should have drawn this a little bit smaller because the areas are much smaller in this case. And then we have the brake paddle. This is the brake paddle, and this is a cylinder. Another cylinder, of course, this is the brake cylinder. So this is connected to a brake shoe. Now, this is the drum. I will kind of go over this in a minute. So let's try to put the numbers first, and then let's focus on what we need to find, and then I'm going to go over what it is. Okay? So let's start with the area of the surface of this piston right here. This is a piston. So I'm going to say this side is a master cylinder. So let's say this is the master cylinder. This is the brake cylinder. And for the master cylinder, I'm going to put the area as AM, area of the master cylinder. I'm going to put here area of the brake cylinder. Now, applied force this way, I'm going to call this FB, the brake force. Applied force this way, I'm going to call this as F, or we can say just F. Let's put it F because I don't want to put too many acronyms. If you put too many, it's not going to help you, right? So let's put numbers. What is this? What is this? What is this? And also given to us is the radius of the wheel. Actually, not the wheel, the drum. So let's see. let's say this is R that is given to us. We also have the dynamic coefficient of friction given to us between the shoe and the drum. So this is my brake shoe. And this is okay, first off, let's get the numbers. What is the force here? Applied force on the foot pedal?
44.
I'm sorry?
44.
44. Let's put a foot pedal. So, and what is the area right here for the master cylinder?
1.8.
I'm sorry?
1.8.
1.8, and the units are?
Centimeters square.
Okay, what is the units over here?
6.4.
6.4, and of course the same units. And let's put the other numbers as well. What is the dynamic coefficient of friction? 0.5. And what is the radius?
34 centimeters.
34 centimeters. Okay, I think that basically covers it. Okay, let's look at what really happens here. This is your brake pad. So when you slam on brakes, this is where you would push, right? And of course, there is an oil in, and you have a piston, okay? And then when you push, you increase the pressure in the oil, and that pressure gets transferred to the other end of the piston. And on this side, you have another piston. So in other words, from this piston, the pressure gets transferred through the fluid onto this piston. So the force transfers into this side. Okay? So what would be the fluid inside this? Any guesses? You have oil in the car. You have what else? You have transmission fluid. Yeah, there you go. Brake fluid. This is exactly what it is. This is brake fluid. Okay? So when you check the fluid levels, this is what you check, whether you have enough brake fluid. Okay? So what else? Okay, let's look at what really happens here. Now, this is what we call the shoe. So over time when you drive the car, the brakes will get worn off. The shoes usually are the ones that gets worn off most of the time. So you have a drum, a metallic circle, hard metal, and then you have a shoe that kind of sits right next to it. So this is our drum. This is inside each of the wheels. Okay? So what we do is this, we apply a force. So this is our drum. Drum is made from steel. Hard stuff. It has to be. Okay. So when you apply force, what happens is this. You are applying a normal force. Now, of course, this case, the normal force is the brake force. And then you have a friction between the drum and the shoe. Again, this is our drum. This is our shoe. Okay? So, as you apply the brake force, then because of the coefficient of friction, we have a frictional force. Okay? We can calculate the frictional force by normal force times the coefficient of friction. Okay? In this case, it will be our brake force. Okay? Because the frictional force is always going to be opposite to the direction of motion. So let's say your wheel is rotating this way. So the car is moving this way, right? So car is moving this way. This is the motion of the car. The wheel is rotating this way. So as the wheel rotates this way, the car will gradually move to your left, right? So as the wheel rotates, when you apply the brake force, the frictional force is always going to be against the motion of the wheel. So the wheel is rotating this way, the friction will try to stop the movement of the wheel. So it has to go this way. So this is our frictional force right there. So how do we increase the frictional force? Any guesses? How do you stop your car faster? Push it harder. You brake harder, right? So in other words, if I increase FB, guess what? If I increase FB, this has to go up, right? If I increase this, what happens to this? Goes up. So this is pretty much what you do. If you don't have any force, which is where you're not pushing the brake pedal, the car won't have a frictional force, and basically you will either move on the same velocity, or of course you will accelerate by pressing the gas pedal, right? So now, of course it will depend on the brake force right here. So now the question is, what is the torque from the frictional force? Now, to find the torque, we have I should kind of draw this towards the center. Let's try to draw this towards the center and it will be better. So my force, I'm going to kind of draw this like this. Okay? So, the radius of the wheel, actually, radius from the drum to the center of the wheel is given to us, which is R. Okay? We have a force acting, a tangential force acting down. Okay? And force acting and trying to stop a rotation is what? If you have a rotating body, you have a force like this. This is the radius. This is our force. So this body is rotating right now. In this case, it's not stable, it's not stationary. The wheel is rotating. So when you apply the force, what will happen to the rotation of the wheel? It will slow down. So in other words, what happens to omega? Omega naught to omega, what happens? It decreases. So in order to decrease omega, what do we need? We need an angular acceleration. Remember the linear qualities? We have, this is initial velocity, final velocity. If you want to change the velocity, what do you need? Acceleration. If you need to change the angular velocity, you need angular acceleration. In this case, this will be linear acceleration. And here you have a circular motion, so you need the angular acceleration. So in order to change the velocity and have an acceleration, what do we need? Force. Now if you want to change the angular acceleration, what do we need? Torque. That's exactly right. So we need F, and here we need a torque. Always remember one from the other, guys. Don't try to remember everything at once. See, I always build from linear and go back to the rotation. This is what I do. Okay? So now, I need this guy to reduce the angular velocity. In other words, make the wheel stop rotating. Make the wheel stop rotating. In other words, that will stop the car moving forward. That's the idea. So now, in order to get a torque, I have a radius, I have a force. In this case, I should draw the simple force because this is my frictional force right here. So how do I calculate the torque? How do I calculate the torque in this case?
I alpha or F.
RF, that's exactly right. RF. I totally agree to what you're saying, but the point is that in this case, this is given directly to us, we will go with that. Okay? RF. That's exactly what we have. So if I have this frequency, the force, frictional force, and then of course the radius right here. So that basically means I can calculate my torque from radius times the frictional force. Right? Now we have to go one step at a time. We have to find this guy right here. Find this guy. Once I find this, I can apply into this. I can find this, of course. That gets figured out. And that goes over here. We can figure the force. We can use the frictional force to figure out our torque. Step 1, step 2, step 3. Three-step process. We need to find the force FB right here. That would be our normal force. This is our normal force. And if we have the normal force, apply the normal force to the frictional formula. So we have the ability to find the frictional force. Use the frictional force over here. Find the torque. Step at a time. Right? So now, let's look at this and go through this one step at a time. So always remember, if we are changing velocities, we require acceleration. Acceleration means there is a force. Changing angular velocity requires angular acceleration. That means it requires a torque. It has to be there. If it's not there, you won't have this change. Okay? So, okay, I feel like I see kind of question marks. No question marks? If you don't get this, at least stop me and let me go over with you, because the thing is, you will have this in the exam. Another thing about physics is that, just imagine, this is Pascal's principle, where the force is getting transferred through a fluid. This is what the problem is about. But think how many parts are there. Just think. You have the force, and then you have to use the formula to find the friction, and then you also have to use the torques. You have to look at your forces, how the forces are set up. All of these comes into play. So the fundamentals always going to be there in any problem you solve. There's now no way that you can avoid it. It's going to be there. So just to give you a heads up. So at least if you don't follow, just stop me, or at the end of the class or something, ask and get this screened out. Make sure that you understand everything. Okay? So now let's see. So we got to figure out first force, FB. And then we have to figure out frictional force. Use the frictional force to find the torque, R times F, and then find the torque. Steps. Okay. Let's use Pascal's principle. Pascal's principle states that if you have a system where you have a continuous fluid, incompressible fluid, and you have a piston on one side, piston on the other side, there's a relationship between the two forces that combines the areas of the pistons. Okay? So in other words, the pressure gets balanced on both sides. This is the fundamental, requirement. So now, how do we put this in formula? So we have F1. In this case, I'm going to put this as F. And this side, the area underneath is AM. And that should be equal to the same ratio on this side. This side, my force is FB, brake force. Okay? I should be careful when I'm using this name. Just for this problem, I'm using this particular name that probably may have a special meaning to it. What I want to find here is the normal force you are applying on the shoe, and in other words, the shoe that end up applying on the drum, normal to the direction of rotation. So the rotation is like this. You are applying this force normal to the direction of rotation. Okay? So now let's see how do we get this. So we have, on this side, we have an area of AB for the area of the piston. Okay? So these are two pistons. Okay? So now, what is our unknown? FB. So if I can isolate FB, all I need to do is multiply both sides by AB, and then I have FB. So I have AB divided by AM times F. So I'm going to put the numbers, I'm going to stop, and I'm going to let you do the calculation. So AB is 6.4 centimeters squared, 1.8 centimeters squared times 44 Newton. So now, quick question. Can I use these units as it is? Centimeter squared on top, centimeter squared on the bottom. Yes, why? They cancel out. They cancel out. That's why. If they don't cancel out clearly like this, you should always convert to the standards. In other words, meters, kilograms, seconds. Okay? So, what is the force, please? I'm sorry? What is FB?
156.
156. Everybody agrees to that? I've done that in multiple, single step rather than going on multiple steps. 156. 156. What's the units? I'm going to erase this. If you want to write it down, go ahead and write it down. I'm going to erase it soon because I need to use the same space. Okay. Good? Okay. So, once we have this, let's just walk in the park. Now we have FB, we need to figure out F. Frictional force. Our normal force is applied by this shoe on the brake drum. So that's our normal force, right? So now, the frictional force is going to be mu times FB. The formula that I'm using is this formula that you have seen. F equals mu times N, normal force. Okay? Now focus very carefully. These steps are very easy. The first one is the hardest one, but let's focus. So this is, if I write with the symbols I have, that would be FB, and then this is my force. Frictional force. Frictional force. Now, what is mu? 0.5. And then of course, what is FB? We found out 156. Guys, could you please find me a number? 78.2. This is my frictional force. Now, I got what we need for the frictional force, and then I need to find the tau. In other words, torque applied on the drum by the friction. Okay, this force is humongous, guys. Usually, of course, when you are driving slowly, it's okay. But if you look at stock cars like NASCAR racing or in other words Formula One, you may have seen these brake shoes sometimes glow red. When they corner, they press them so hard, they glow red. And in other words, they have to use special ceramics. Otherwise, they melt and break. It gets so hot because of the friction. It does so much work because of this frictional force that they get so hot they start glowing. I don't know whether you have seen this, but I have seen it, and it's scary actually. Okay, so I mean, of course, when we are driving, let's be honest, unless you're driving like one of those race car drivers, which I hope not, then it won't be like this, right? And of course, you will end up destroying your brake pads. They won't last that long at all. My suggestion is don't, right? So the point is that this frictional force can be huge, and it will end up heating this pad significantly if you apply it. Now, torque. Torque is what? Torque is R times F. R times F. What is your R? 34 centimeters. Now, can I use 34 centimeters as it is, please? No. That's right. So that is going to be 34 meters. And what is F? Is this 78.2 newtons. Can you please give me a number? 26.5. What it is? Newton. Okay. In reality, you have a booster in a car. Most of the cars, you have a booster. We in fact boost this pressure. As you apply your brakes, the force is going to get boosted inside. But in order to work, in order to have brake force getting boosted inside this system, you need to have a car running. In other words, the engine has to be running. So in other words, if you want to stop a car, at least the engine has to run while you're stopping, because that would make it easier for you to brake.
Without that boost,
It's hard. Exactly. It's going to be very hard. Very hard. That's right. So now, let's move on to. Now, if you don't follow any of this, please ask, because I'm telling you right now, it will be asking and getting this figured out, although it might not be your cup of tea, is 10 times better than sitting in the exam and figuring out what am I going to do for another 1 hour, right? You don't want to be there, right?